100 feet above the river, a single inch of Bessemer steel begins to deform. The internal pressure crests at 120,000 pounds per square inch. A microscopic fracture propagates along the grain of the metal, and then a 2-pound rivet shears off its housing at the speed of a bullet. The antagonist in this environment is gravity. It is a relentless, static downward force vector attempting to pull any mass spanning a void directly into the earth. For thousands of years, engineers combated this downward pull through sheer mass. 19th century masonry relied entirely on compression, stacking heavy blocks so tightly that the resulting friction locked the structure into place. This photograph of the old Bridge of Forth illustrates the physical cost of that logic. To support a walkway over a relatively narrow river, builders had to construct massive, dense stone arches that occupy nearly as much volume as the empty space they span. This creates a mathematical dead end. As you attempt to cross wider spans, you need more stone. Eventually, the stone becomes so heavy that it crushes its own base before it even reaches the opposite shore. Scaling up stone was a physical impossibility. To bridge the widening gaps of the industrial age, engineers had to invert their entire approach to structural mass. The solution arrived in the form of a chemical shift. The Bessemer and open heart processes stripped the impurities from brittle iron, producing high-tensile steel alloys with precise, predictable tolerances. This photograph captures the scale of an early 20th century steel mill, where liquid metal was rolled into modular beams. Infrastructure was no longer harvested from a quarry, it was manufactured in a factory. High-tensile steel gave engineers a new tool: tension. Unlike stone, which can only be pushed together, steel can be pulled apart with massive force without snapping. This geometric shift moves structural design away from solid mass and into invisible forces. A heavy masonry arch is replaced by a wireframe of steel cantilever arms, where tension and compression vectors flow through a lattice of thin girders. We call this steel logic. Gravity is no longer fought with brute weight. It is outmaneuvered with pure geometry and precise mathematics. The material allowed for spans far beyond the physical reach of masonry, but it introduced a severe vulnerability. If a single mathematical calculation regarding those invisible forces was wrong, the entire lattice would fail. Before engineers could test this new math in the air, they had to secure foundations deep underwater. A massive steel tower requires a bedrock base. To reach the bedrock, crews used pneumatic caissons. These were massive, airtight wooden boxes sunk into the riverbed. Compressors pumped air down into the box, forcing the river water out so men could dig through the mud at the bottom. This required precise biological math. The internal air pressure inside the caisson had to exactly match the external hydrostatic pressure of the river above. If the air pressure dropped, the river would instantly flood the chamber. But the human body cannot withstand rapid depressurization. Workers returning to the surface developed caisson disease, or the bends. Nitrogen bubbles formed in their blood, causing severe joint pain and paralysis. The human physiology failed long before the engineering did. This photograph of the Brooklyn Bridge construction shows the scale of the work. Tiny silhouettes of workers manage thousands of tons of tension. Chief Engineer Washington Roebling spent so much time in pressurized caissons that he was permanently paralyzed. He oversaw the remainder of the construction through a telescope from his window, while his wife, Emily Roebling, managed the daily engineering on site. The caissons proved that the physical limits of the human body had to be factored into the structural mathematics of the bridge. The high casualty rate and the unknowns of early steel prompted an extreme defensive design approach on the Brooklyn Bridge. The Roeblings utilized a hybrid system. They installed diagonal stay cables radiating directly from the towers, running alongside a traditional vertical suspension cable system. Here, cyan arrows show vertical suspenders pulling the deck up in tension, while red arrows trace the load transferring into downward compression through the stone towers. If a diagonal stay snaps, vertical suspenders instantly recalculate to absorb the dead weight. The structure survives. This over-engineered, cautious logic kept early steel bridges standing. But as the 20th century progressed, economic pressure demanded longer spans with less material, pushing engineers to strip away the safety nets. That ambition peaked with the Quebec Bridge project. The goal was to build the longest cantilever span in the world, stretching 1,800 feet across the St. Lawrence River. To understand what went wrong, you have to look at the dead load, the absolute weight of the raw steel structure itself, before you add trains, cars, or wind. Cantilever bridges face a compounding physics problem. To reach further across a river, you have to add more steel. That new steel increases the dead load, which means you must add even thicker steel at the base to hold it up. Lead engineer Theodore Cooper lengthened the main span of the bridge by 200 feet late in the design phase. However, he failed to recalculate the original dead load estimates to account for the extra mass. This historical document captures the massive lower framing of the cantilever arms before the collapse. Every girder seen here was significantly heavier than the mathematical models accounted for. The physics localized entirely on cord A9L, a single massive steel beam near the base of the southern anchor. It was forced to absorb compressive vectors it was never designed to handle. In August 1907, the compression load surpassed the Bessemer steel's yield strength. The metal physically bent under its own weight. Once the mathematical lattice broke, gravity took over. In less than 15 seconds, 19,000 tons of steel buckled and violently collapsed into the river. The Quebec disaster established a baseline. The incredible tensile strength of industrial steel is completely useless if the underlying vector math is flawed. Engineers eventually realized that fighting forces with perfectly rigid steel was the wrong approach. To survive dynamic loads like gale force winds or heavy traffic, a bridge actually needs to move. Under immense environmental pressure, absolute rigidity leads to brittle failure. Controlled flexibility, allowing the metal to absorb and dissipate the energy, leads to survival. This photograph from the construction of the Golden Gate Bridge captures the height of this flex logic. The worker is looking down the massive suspension cables that support the highest bridge towers of their time. To ensure it wouldn't tear apart in Pacific winds, engineers built extensive physical scale models at Princeton University in 1933, simulating exact vertical load deflections. This wireframe animation demonstrates how that deflection works in reality. The bridge deck isn't static. It is designed to safely flex up and down by several feet, converting the kinetic energy of traffic and wind into harmless motion. These massive, complex deflection vectors were calculated using tools like this vintage slide rule. They mapped the precise flex of millions of pounds of steel using nothing but logarithmic scales printed on wood. The greatest megastructures of the 20th century were calculated entirely by hand. They are masterpieces of analog theoretical computing. Steel logic is an invisible framework of tension, compression, and deflection. It is a mathematical theory validated by decades of physical trial, error, and disaster. This photograph of construction workers standing casually on exposed girders reminds us of the audacity required to physically build these abstract equations into reality, hundreds of feet in the air. Every time we drive across a modern suspension bridge, we are trusting a century-old logic problem solved by engineers who had no computers. They looked at the downward pull of gravity, mapped the invisible forces, and built a machine that holds a locomotive suspended in midair. We have mastered the static physics of bridges, but our most critical dynamic infrastructure, the electrical grid, is currently being pushed past its own mathematical limits. The turbines that power our world are losing their mechanical inertia, setting the stage for the invisible 50 Hz war.